We were discussing about first order system. We have covered impulse response and step response. Now let's see third test signal as ramp response. Right, so a ramp response is we know ramp is nothing but t of ut, and it will be like this is our ramp function, right? So and when we take its Laplace transform, it comes out to be 1 by s square. This is both way, right? So let's analyze this thing. We know cs is equal to rs by st plus 1, right? So how I can write 1 by s square into st plus 1, right? Now if I do its partial fraction, I hope you can do. I will move quickly, and taking its inverse Laplace transform, what I'll get is t minus t multiplied by 1 minus e to the power minus t by t ut. That is simple partial fraction, and then you can take its inverse Laplace. I leave it to as an exercise for you. Okay, so this is the response, ramp response. Now what I can write is, now next thing is error. Error is defined as et is equal to rt minus ct, right? Et is equal to rt was nothing but tut minus t 1 minus e to the power minus t by t, and multiplied with ut, right? So what I get is et is equal to t into 1 minus e to the power minus t by t, right? So steady state error I can write as limit t tending to infinity, and this is et, right? So what I will get, steady state error, I will get t in ramp response, right? So my steady state error has increased now, right? And fourth response I get is fourth I will talk about. This is not so important. I will leave it to steady state error only. This is how we can find our response. Our unit step response and impulse response are very important. That's why I have discussed them in very detail, and I'm going through very fast here. Next is parabolic response. Parabolic response, right? So how do we, wait a minute, right? So parabolic, what I take, t square, I divide it by 2 for the simplicity. You can take even t square ut, 2 will go upward. For the simplicity I am using t square by 2 ut. Test signal is nothing but parabolic only. It's not going to make any difference, right? And then I can write cs is equal to 1 by s cube and 1 by st plus 1, right? So this is how I get. And if I take its partial fraction and then we solve for it, what I get is ct is equal to t square by t minus t minus t 1 minus e to the power minus t by t, and here it will be closed, and ut for causal system, right? So this is what I got, right? If I calculate its error ETRT minus CT and do some manipulation, then what I get is steady state error is equal to infinite. That means steady state error has been increased more in parabolic response. Right. Now that conclude our discussion of first order system. Now we will move to our second order system. Like it is one of the very important and very frequently used in our control system, right? So what I write, second order system, right? What second order system? We already discussed that it is going to be low pass only. So how I can make a low pass second order system? RL, and this is output taken across capacitor, and this is my second order system. Here it is RT, right? And here I am taking output, and this is I am taking as across capacitor, and it I denote it by CT. Without losing generality, I am taking this as output, this as input, right? So how I can write its transfer function? CS by RS, sorry, let me write CS is equal to input RS multiplied by this impedance, that is 1 by SC, divided by total impedance, that is R plus SL plus 1 by SC, right? So how I can write CS by RS transfer function? I am writing CS by RS is equal to 1, take downward SC, so S square LC plus SCR plus 1, right? So this is my transfer function of second order system. And in general we represent transfer function of second order system as CS by RS is equal to omega n square S square plus 2 zeta omega ns plus omega n square, right? And this is known as gain of system, right? And this is known as natural frequency. Don't get confused between these terms and these terms. These both are different terms. This is gain and this is natural frequency of the system, or I can say undamped frequency, because natural frequency means undamped frequency only, right? So this is my undamped, and this is called as zeta is called as damping factor, right? So if I ask what is what is zeta? Zeta can be defined as zeta omega n divided by omega, right? So what it is? Zeta omega n is actual damping factor, right? And omega n is nothing but critical damping factor. Therefore zeta is defined as ratio of actual damping factor, how much damping system is doing, and critical damping is this omega n, right? Because zeta is 1 known as critical damping only, right? So that's how we define our zeta. Zeta is one of very important characteristic in time response analysis, right? And let me give some example differentiating these two terms, like 10 upon s square plus 2s plus 4, and second one is 4 s square plus 2s plus 4. Now see, these has natural frequency 2 radian per second, this also has 2 radian per second, but here is the difference between gain. So that's what I said, don't get confused between these two terms. This is gain of the system and this is natural frequency or undamped frequency, right? Only difference comes out to be in terms of gain of the system, right? Now let's take an example. First example I am taking, say transfer function is given as s plus 6 divided by ks square plus s plus 6, right? And it is given that zeta is equal to 0.5. Then find value of k, right? Now how can I find? Let's write in terms of standard form. When I take standard form, this comes outside, so we get s plus 6 by k, and this is s square plus s by k plus 6 by k, right? And if I compare this thing, this characteristics equation with my general transfer function, and here is something like as I write, and s square plus 2 zeta omega ns plus omega n square. If I compare these two characteristic equation, so what I get is 2 zeta omega n is equal to 1 by k. Now I have already got zeta, so 2 into zeta given 0.5 omega n is equal to 1 by k, right? So omega n comes out to be 1 by k, right? This is 1 by k, but if I compare, this comes out to be with this omega n is equal to root 6 by k, right? If I equate these two terms, what I get is 6 by k. Therefore k comes out to be 1 by 6, right? This is what we want to find, right? So and what I write, omega n is equal to 6 radian per second. Fine. Now this question is done. Now let me take cs by rs was equal to 1 by sc plus sl plus r plus 1 by sc, right? So what I can write is s square lc plus scr plus 1, right? So how can I write this thing? 1 by lc in terms of standard form, s square plus s c got cancel, sr by l and 1 by lc, and in general I have omega n square s square plus 2 zeta omega ns plus omega n square, right? So if I compare these two terms, what I get, omega n equal to 1 by root lc, right? And what I get, zeta is equal to r by 2 root c by l. This is very important, you should remember these standard thing. Fine. So this is omega n, very important, and this is how zeta you get from a simple low pass RLC. We have taken here low pass only because we know control system are generally our low pass system, right? So next we'll analyze damping methodology, analysis of damping methodology. Right. We have this thing cs by Rs equal to omega n square s square plus 2 zeta omega ns plus omega n square. This is our standard second order system. Now we have seen that characteristic equation characterize the system, right? So I write characteristic equation s square plus 2 zeta omega n s plus omega n square is equal to 0. This is my characteristic equation. Now I want to find its root. How I can find its root? By using standard form. I can write minus 2 zeta omega n plus minus 4 zeta square omega n square minus 4 omega n square divided by 2, right? And after solving I get s is equal to minus zeta omega n plus 4, sorry, this I can take out omega n and zeta square minus 1. Let me write it again. S is equal to minus zeta omega n plus omega n under root zeta square minus 1, right? This I got the locations of pole. Like this location in S plane vary depends on zeta values and omega n values, right? Generally we will be varying zeta values. According to the damping required we will be varying this. Now zeta vary from 0 to infinity, or zeta can vary from 0 to minus infinity. Now if I vary 0 to minus infinity, that is zeta is negative. When zeta is negative, this thing comes out to be imaginary, right? But this thing comes out to be positive, right? Positive side means real parts of the pole are positive. If real parts of the poles are positive, then that means system is going to be unstable. But we don't want our unstable system, we don't want our system to be stable. So this is called negative damping, and generally we will not use this, right? And this is called positive damping. Now in positive damping, it may be real or it may be imaginary. For zeta greater than 1, it is going to be real, right? For zeta less than 0 to 1, it is going to be imaginary, and this part is going to be negative. Now this depends on this value and this value. When zeta is greater than 1, then this may goes to right side of the system, that we will see. Now first case I discuss zeta is equal to 0, and this is called undamped system. And that is we are not doing any damping to the system. Then we will be having two poles as 1, 2. I represent it like this, and when I put zeta equal to 0, this part become 0, this part will become plus minus, this is under root minus 1, then this comes out to be plus minus j omega n, right? So what that mean, at zeta equal to 0, my pole locations are on imaginary axis. Pole lies on imaginary axis when I have a undamped system, right? So this is not a stable system. This is generally called marginally stable. Marginally stable system are nothing but unstable only. But we use these kind of system in our oscillator circuits, but for our control system purposes, these are not stable system, right? We don't desire this kind of stable system. Also, this will be having a sustained oscillation with its natural frequency. That is not desired. Sustained oscillation is not desired in control system. Second thing is when zeta lies between 0 to 1, this is called underdamped system. Now see S1 to when zeta lies between 0 to 1, this will having some value zeta omega n. Now when zeta is between 0 to 1, then this part will have imaginary value, right? So what I can write, plus minus j omega n root 1 minus zeta square, right? So that's how I define it like this, and I show its moment with zeta 0 to 1. Now when zeta is 0 was this location, and when zeta is equal to 1, then this will be 0, this part will be 0, right? This part will become 0, and I'll be having here minus omega n, right? But when zeta is varying between 0 to 1, how pole location will move? Pole location will move like this, and from here it will move like this, right? So this part belong to zeta equal to 0, this part belong to zeta equal to 0, and this part belong to zeta between 0 to 1, right? This is called undamped. At undamped pole locations are here, it is underdamped system, zeta value 0 to 1, right? And here it is zeta equal to 1. This is called critical damped system. Our third system is zeta equal to 1 is our critical damped system, right? So here poles are complex conjugate, like here it is pole, here it is pole, here it is pole, then here it will be pole for some value of zeta. But in critical damped I have purely real poles, and when it is undamped I'll be having two complex conjugate pole but at imaginary axis, right? So this part will be here, this system will be stable. This is also stable, but this is marginally stable. Now next case comes when zeta greater than 1. Now when zeta greater than 1, let me take it on separate page. When zeta is equal to 1, then this part is real, and this part is also real. So pole will move, let me draw it here like this, and this was the for some zeta up to zeta value. Now when I'll be increasing, now see, minus zeta omega n plus minus root zeta square minus 1. So S1 will be equal to minus zeta omega n plus root zeta square minus 1. S2 will be equal to minus zeta omega n minus root zeta square minus 1. Now as I am increasing zeta, this value is increasing, this value is also increasing in negative, right? So S2 will move this way. That is good for the system because poles are moving away from this imaginary axis. But at the same time, as zeta is increasing, this part is increasing, and which will decrease this part. So overall S1 will decrease in the sense in this side, actually it is increasing. I am just saying magnitude wise it is decreasing in this direction. That is bad for the system, right? It is going toward instability. So generally zeta greater than 1 is not used, right? So we will use only zeta less than 0 to 1, right? So this part belong to overdamped system, this part belong to critical damped system, this part belong to undamped system, this part belong to underdamped system. So our generally we use an underdamped system, not even critical damped. Except for the oscillator application, we don't even use critical damped. We generally use this system. Why we use this underdamped system? Like, as I am going this way and this way, see, I know time constant is equal to 1 by zeta omega n. This is time constant of a system. Now when I am going this way, my zeta is increasing. Zeta is increasing, that is very good for the system. But as soon as my zeta is increasing, like zeta is increasing, then time constant is decreasing. Then if time constant is decreasing, then bandwidth all increases. If bandwidth increases, then my accuracy will decrease of the system. So generally we cannot use here. First of all, if critical damped system is this can be like over damped anytime, so I will not be I cannot use it here. So I have to be somewhere between this region, like this region will be preferable. Like if I am going this way, like if zeta is less, then I'll be having very less damping, oscillation will be there. So preferred region of pole location is this. And generally sometime it was asked, generally 0.4 to 0.7 is the best range for zeta to use any system. So poles of the location generally we want in this region where zeta lies between this range, right? This is not standard, this can vary depending on the application of the system. So this is not necessary that we have to take this value, but that depend on the kind of response we want. First of all, let me mention some point. Undamped system is unstable system, not desired for our control system, right? Second is critical damped system is quite impractical because it may go to over damped anytime, so that is also we will not use. And over damped system become slower with time. Why? Because as this pole is moving away, but this pole is moving toward the imaginary axis. When we will see that dominant pole concept, that like if it has two poles, like one is moving this way, one is moving this way. Now at some point of time this pole dominates, and this pole will be out of the picture very soon, right? So what happen is, theoretically an overdamped system is second order system, but practically that will behave as first order system. And behaving like a first order system means it is very sluggish. My response will be sluggish in that case. So even overdamped system we will not use. And underdamped system, I have discussed that they are very good system and practical system. That's why we will be using our underdamped system in case of control system. Now let me define time constant. Time constant of undamped system is going to be infinity, right? Because it is not going to be settled at any time, right? And underdamped system time constant is going to be 1 by zeta omega n, right? And for critical damped system it is 1 by omega n. Fine. So if I represent T of undamped system is greater than underdamped system and critically damped system, right? So we will not talk about overdamped system because that depends on pole location, dominant pole thing. So there are other factors also that may or may not behave as second order system. That's why I am not mentioning time constant of overdamped system, right? Now let's see one more thing. Let me draw pole location graph. This is my sigma axis, this is j omega axis. That's how was my pole location diagram for different value of zeta, right? So what happen is, if this is this I draw it, this point is minus zeta omega n, right? And this is my omega d, my damped frequency, omega d. We know omega d is nothing but omega n under root 1 minus zeta square, right? So this is my omega d, and this part is omega n, and generally we write this thing as phi. That is very important thing to determine characteristic, and while designing system this thing become very important. So how I write is sine phi is equal to omega d and divided by omega n, this value, right? So how I can write is sine of phi is equal to root 1 minus zeta square. So I can write cos phi is equal to zeta, right? So as phi increases, cos phi decreases, zeta decreases. That means if phi is increasing, like this line is more inclined to vertical axis, then zeta value is decreasing. Here zeta is decreased. That is what I can identify by using this phi concept, right? So that actually that is the main characteristic when we will be designing our compensator and controller. Then we will see how it is very helpful. So let's discuss one problem. Question: given pole 0 of second order system is given this, and here pole location, there are two complex conjugate pole, and let me draw their angle, and angle it is shown, and these are 45-degree angle, right? This value is 1. Now we need to find its transfer function. We need to find in terms second order system it is given. So how I can write phi is equal to 45 degree. Here it is solution, it is phi is equal to 45 degree. Now cos phi is equal to cos 45 degree, that is 1 by root 2, right? So zeta is equal to cos phi means zeta is equal to 0.707, or I can simply write 1 by root 2 for simplicity, right? And this part is given 1. What this is nothing but omega d, our damped frequency. So I can write omega d is equal to 1. Omega d is equal to 1. Omega n under root 1 minus zeta square is equal to 1. So I can write omega n under root 1 minus zeta square is nothing but 1 by 2 is coming out to be 1. Omega n is coming out to be root 2, right? And so how I can write my transfer function? Transfer function I can write as 2 divided by s square plus 2 zeta is nothing but 1 by root 2 and omega n is nothing but root 2 s plus omega n square 2. That is 2 transfer function is equal to 2 by s square plus 2s plus 2. That is my general transfer function, right? So that complete our discussion of this question. Now let me talk one more important thing is we have seen pole location. If I go like this and say this thing, this. Now if my location of pole is like this, right, this is known as constant zeta locus, right? And second thing is, if my pole location moves like this, this is called as constant omega d, locus, right? And third, if my pole location moves like this, this is my constant alpha. Alpha is nothing but zeta omega and alpha locus, right? These things are little important. You should remember very fastly what constant is here to solve question with more speed in exam. So you should be very comfortable. Have a look, spend some time on this is very simple, that is a constant zeta omega n, and here it is constant omega d all, and here it is zeta omega n is zeta is constant here, right? So that complete our discussion of damping and time constant and our pole zero location. Now we will look at impulse response of second order system. Impulse response we have seen in case of first order system also. Now we want to analyze our second order system, so we will look at impulse response first of all. So impulse response delta t has its Laplace transform as 1. So how I can write Cs is equal to omega n square by s square plus 2 zeta omega n s plus omega n square, right? So first of all I need to separate these things. In this quadratic equation I need to put partial fraction also, so I will not go into that. Let me write first of all, we know that e to the power minus at sine of bt multiplied by ut has Laplace transform of b upon s plus a square plus b square, right? And second formula is e to the power minus at cos bt ut has its Laplace transform as s plus a on s plus a square plus b square, right? Now I try to manipulate these thing, I get omega n square. Let me what I can do, s plus zeta omega n square, right? So when I do this, zeta square plus omega n square I am adding additionally, so I can write omega n square minus zeta square omega n square, right? And cs I can write as omega n square s plus zeta omega n square plus if I take omega n common, omega n under root 1 minus zeta square whole square. This is nothing but my omega d square, right? So how I can write, cs is equal to omega n square s plus zeta omega n square whole square is equal to omega d square, right? So now I have s plus a square plus b square, right? And b square, or so I need here b to have this formula. So what I do is omega d I multiplied by omega d and divided by divide also by omega d, right? So what I get is cs is equal to 1 upon root 1 minus zeta square, and omega n will also come because here omega n will cancel out, and I get omega d upon s plus zeta omega n square plus omega d square, right? This is what I got. Now if I apply its inverse Laplace transform, then this formula will be used, right? So what I get is, taking inverse Laplace transform, I'll be getting omega n on root 1 minus zeta square, and e to the power minus at means e to the power minus zeta omega nt, and this is nothing but sine omega d t, and this is multiplied by ut for our causal signal, right? So we know from our first order system that impulse response must be less than infinity, its integral, right? This condition we know. So from here we get omega n upon under root 1 minus zeta square, and here it is 0 to infinity. I am taking e to the power minus zeta omega nt sine omega d t dt, and it should be less than infinity, and in fact it is going to be less than infinity. Why? From here if I have to draw its response, see what I got is ct is equal to omega n root 1 minus zeta square and e to the power minus zeta omega nt sine omega dt multiplied by ut, right? So how its response will be, like this, going upward. Let me draw exponential decrease first. This will be decreasing like this, it will be decreasing. So how it will behave like this, it will be going like this, going like this. This is impulse response of second order system, right? That's how it will be behaving to unit impulse response, right? So how I can write, this is for zeta less than 0 to 1, right? If zeta is equal to 0, simply I put in this equation, put zeta is equal to 0. What I get is ct is equal to omega n Ct is equal to omega, and this part goes to 1, this part goes to 1, and I'll be having sine omega dt will be equal to omega n in that case, and ut. So I'll be having this kind of response. Right, so this is called our undamped system. Right, and for this is for undamped, and if I talk about zeta is equal to 1, right, so if I put zeta is equal to 1, this part will go to 0 0, and this is like exponential decay, because this part will using LHO hospital. Don't say this is 0 by 0 form, we can always use LH hospital to find that thing, and it will be having a exponential decay like this, right? So this is for zeta equal to 1, and for zeta greater than 1, I'll be having high time constant for dominant pole system. Like we have mentioned that like this is my overdamped. I'm talking about this. Let's say this become dominant and this become out of picture in system, right? So this will be dominant, so it will be having high time constant. When high time constant means it will be decaying very rapidly. So this is for zeta greater than 1 for our impulse response, right? So this thing completes our impulse response of second order system, and tomorrow we are going to see in step response of the system. Okay, thank you.